So we're going to go through the implementation of signal handling. I know that's a shock given the lecture title, but this is one of those more advanced, more sophisticated areas of operating systems. Some of the facilities that they offer to user applications. We'll do a quick review because, of course, we talk about this in CS24. But basically, signals are a way of exposing this exceptional control flow mechanism into user applications to rely on. And there's a lot of nuances, a lot of difficulties. You have to really know what you're doing even to use signals properly in any more than the most simplistic usage patterns. So that's something that makes it challenging. But you can register a signal handler. We have a couple of different things to talk about. One is that this is actually declaring a type. We had a discussion after one of the classes about this. Sigt here is the name of the type. And what it is it's a type that's a function pointer to a function that takes an int and returns nothing. Okay, so that's what sigt here is. It's a little bit confusing because you're used to type def, the last thing, the last symbol being the type name, but in this case it's nestled in there in between. And then we can use that with signal to register a signal handler to handle a particular kind of signal. And there's a few other things that you can pass in. Remember, there's sig_dfl to get the default handling. Do I actually say this here? No, I don't. But you can also pass in sig_ign, so sig_ign, to tell it to ignore the signal as well. So you could ignore control C's, you could ignore seg faults, you could have really fun time making the craziest program ever. Don't do this, but you could write a fork bomb that can't be killed. And, good luck. The machine will probably grind to a halt if you did something like that. This was the example that we gave in CS24. So we have two signal handlers here. One for sigint, which is control C. And then you also have sigalarm, which just prints out a little message saying hello. And the way that we have it set up is that we generate an alarm signal every second. We set up the first one in main, and then after handling each signal, we go ahead and request another alarm in second, so that basically we generate hellos for a long time. Now, you might remember that you can kill this. I can't remember what the command sequence is. I think it's control / or control M. I can't remember. But there's one of those that sends a sig quit instead of a sig int. And the default sig quit handler is to terminate as well. So it is possible to kill this. And you could always send it a sig kill if you really wanted to terminate it. But this was the idea. Now, there's also sig action, which is far more interesting, because you'll notice that you can specify all of this interesting stuff in the sig action struct, which I'm not going to show you because it's kind of beside the story today, but you can certainly use man to look up all the details. So you can either have a handler or you can have this sig act thing. And notice that sig act takes a signal number, sig info, which describes details of the signal that occurred, and then this fun ctxt thing. What is the ctxt thing? So you have various details here. The ctxt, I'll just say context. This is why we say machine context so much, but this actually points to the register state of the interrupted part of our user process. So that contains all the registers. It contains a few other details. It includes the instruction pointer, and it includes the stack pointer and things like that. So we can actually modify that stuff and modify what will happen in our process when we return back from our signal handler. And this is very important if you want to implement a user space threading library, for example. Remember that this is actually exactly how Lab 7 works in CS24. We use this to implement a forced context switch from one user thread to another user thread. Okay, then there were these bit vectors, which we talk about rather significantly in CS24. You have a pending bit vector, which just says a signal of this type is pending delivery. And remember that we only have one bit for each pending signal, so if we have multiple instances of a signal occurring before I go ahead and receive them, then I'm only going to see one signal of that type delivered. So I can't use this to tell how many things happen. I can just use it to tell at least one instance of this kind of thing happened. The block bit vector is helpful because it makes sure that when a signal is being delivered of a particular type, it can't be delivered more than once, overlapping or concurrently. So like I say here, you can have a signal that's blocked and pending. When you deliver a signal, it automatically becomes blocked until the signal handler returns, and then it's automatically unblocked again. And so what you end up with is something that looks very similar to how hardware interrupts work. Because remember, hardware interrupts have to be acknowledged before you'll get another interrupt of that type, which is very similar to the blocked bit vector. And the pending bit vector is very similar to if you have interrupts disabled and then you decide to re-enable them and then suddenly you start getting interrupts. Okay, so similar mechanism, very similar to what we have in the hardware level. Now, are there any questions about signals at this point? Because we're going to start getting into all the nuances of how this works. Okay, it's pretty straightforward. I think you would all agree. So the real question I wanted to look at today is how does the kernel actually provide signal handling to user processes? And there's a number of questions to explore. One is, when do we actually deliver these signals? Because you could have a situation where the process is running, or it might be ready, or it might be blocked at any of these times when a signal is delivered. Remember, one process can send another process a signal, or the kernel can send a process a signal, and so forth. If I have multiple signals pending, how do I handle that situation? So how do I make sure that there's, all of these things are dispatched in a reasonable way? And of course, there's a lot of other questions that we'll explore as well as we go through this, but there's one area we exclude sort of intentionally, which is how this works in the context of multi-threading. Because if you have kernel multi-threading support, it turns out that in POSIX you can actually say, I don't want this thread to receive any signals. And that way, that thread will never actually run a signal handler. So you can basically set it up so that one thread only ever handles signals or whatever. You can actually have different threads handle different kinds of signals as well, if you'd like to do that. So it's kind of an interesting detail that you can do with multi-threading. Now, if you have something like a kill, sig child, you can see that the process that is going to receive a signal isn't always necessarily the one that's running when the signal is delivered to the process or generated to send to the process. So the kernel makes a distinction between generating the signal and delivering it. And generation is basically about updating the data structures of that process to say there is now a signal that's going to be delivered to that process. And delivery is about the kernel making sure that that signal is actually delivered to the process, perhaps by running a user mode signal handler, maybe by terminating the process or suspending it or whatever the signal's response requires. And there may be a lot of time between those two steps. Now, we talked about pending and blocked already, which you can always use to tell if a signal is ready to be delivered. For example, sig kill might be recorded this way, sig stop or sig conf might be handled that way. But you have a couple of other details as well. You can see you have a linked list of signals which are ready to be delivered. That's under signals, and you can see it's just a sequence of siginfo objects. And then you also have sig action. So what do I do based on each signal? Remember, each signal has a number associated with it, and that's just an index into this array, and the entry in the array says this is how you handle that signal. Okay? And there's a lot of other details that can be stored there as well, besides just what to do, because you can have some signals block the delivery of other signals while they're being handled. You can have some signals be delivered at a higher priority than other signals. All of that stuff can be configured through the sig action call. So all of that stuff has to be squirreled away so that the kernel can use it when it's delivering signals. So there's a specific function that's invoked, and it actually is specific in the name, it turns out, that goes ahead and updates a particular process's details to say this signal is now being delivered. And it is surprisingly sophisticated for what needs to be done, because you may already have a pending signal of that type, and if it happens to be a non-real-time signal, then If it's already in the queue, then it's not recorded again because we just need to record that there's one instance of that type. There are special signals that can actually be recorded, and it'll make sure that every instance of that signal will be delivered. We call them real-time signals, but most signals are not real-time signals, so there's sort of a special subclass of those. So that's one thing. If the process is already ignoring that signal type, then don't even update the data structure, so you can see that that will occur. Obviously, there's certain ones that can't be ignored, like sigkill, so that would update the process's state anyway. But if the process is already ignoring the signal, then it just goes ahead and doesn't do anything. Okay, then these things all occur just as we would expect. One of the interesting things, I'm going to probably try to talk as little as possible, but if the process is already blocked or suspended at this point and it gets a signal and it needs to respond to it, then now we say it's actually not blocked anymore because now it should be able to run. So we go ahead and move it into the ready state because we do need it to respond to the signal. And there are a few signals that don't get added to the signal queue, which is kind of interesting. You'll notice that they tend to involve signals that modify the scheduler state of the process. So sigkill says go straight to terminate. Don't do anything else. Don't pass go. Don't collect $200. And then you have sigstop, which moves it from the scheduler as well. Even if it's ready, it moves to a suspended state. So these things can be enforced by the kernel immediately. So we don't even store them in the queue. We just go ahead and update the process's execution state. Okay, so that's generation. When you need to deliver a signal, clearly that process that's receiving the signal needs to have the CPU. Because if it doesn't have the CPU, then we can't actually do anything on its behalf. So that's the reason for that. And basically, remember that we typically have scheduled process switches. So toward the end of doing whatever we are in the kernel, we call the scheduler, we say who gets to go next, we pick somebody to go next, and then this extra work happens right before we end up going back to the process. We say, does it have any signals that are pending that need to be delivered? If so, they're handled. If not, then we can just skip that part and go back to the user process. And there's two ways that they can be handled. One is the kernel handles it for us. So we either have a default action or we ignore it. That's easy enough. Or we have a user mode handler that has to be invoked to handle the signal. So the real process ends up looking a lot more like this. Okay, so we have this basic loop in here which says, do we have a pending signal? Yes. And then you'll notice that kernel handled signals and user handled signals are handled a little bit differently. So if it's kernel handled, we handle as many as we can. If it's user handled, we only handle one of them. Okay, and we do this weird little thing where we step back into the user process, deal with the signal, step back into the kernel, and then step back into the user process. We'll talk about why in a second. Okay, so this is all basically what I just talked about. I want to mention also that Linux 2.6 is a simple implementation of signal handling, which is kind of funny because they modified it quite significantly going forward. They even introduced this thing where you can open a file descriptor to receive signals on if you don't want to use the default signal delivery mechanism. So you can just create a, it's called signal FD. You call that, you create a file descriptor, and the kernel will send you signals on this file descriptor instead so that you can handle them whenever you want, which is kind of an unusual thing. But so this is a little bit outdated, but it's very straightforward to understand. This is how I would do it if I were implementing this in a kernel. Okay, delivery challenges. So yeah, first of all, we have the signal handler being, doing its thing and then jumping back into the kernel. Why do we do that? Well, because we had a user process context that was interrupted by the signal being delivered, and we need to restore that. So that's why we have to jump back into the kernel. We need to ask the kernel to do that for us. Also, signals on preemptible kernels need to be able to interrupt system calls. So you're in your read operation, you're in your write operation, the process is blocked or whatever. You need to be able to interrupt that. So the signal delivery mechanism needs to be able to interrupt a system call. What complicates that even more is that signal handlers can actually make system calls as well. So I made a system call, I'm blocked, and then a signal goes off, and in my signal handler, I go ahead and try to run some operations. So that is another thing that complicates this mechanism. And then probably the weirdest thing is that you can actually long jump out of the signal handler back into the user process, which you might say to yourself, how in the world does that affect this whole picture? Okay, so these are pretty significant challenges to deal with. So just talking about how Linux 2.6 does it, we have a loop like I have here in our little flow diagram, and it looks for pending signals to handle. You'll notice that some signals, funnily enough, cancel each other. So if you have a stop and then a continue, both in your pending queue, they basically annihilate each other, and you don't even have to do anything. Because if stop moves you into the suspended queue and continue moves you back into the ready queue, why do anything? Just go ahead and consume them. You'll have various other things that can happen as well. If there's no more pending signals, then the kernel returns to user process. And of course, if a pending signal is found, it's removed from the pending queue. This is kind of important that you'll notice the signal is removed from the pending queue right at the beginning of this mechanism. That becomes important later on, so I just want to make sure that I point that out. It's possible that the signal is being ignored. Now, I couldn't think of exactly what situation might cause this, but remember that signal delivery, or I should say signal generation, can have ignored signals discarded at that point. Signal delivery can also look at ignored signals, so I don't know what would cause a signal to be ignored after it's been generated already, but I suppose a signal handler could ignore another signal, and so you might have that situation that causes it. Okay, so then we see, do we need to take the default action? Now you'll notice, look at the default actions here. We have terminate, dump, ignore, stop, and continue. These are the default actions that Linux basically takes. And I should really say Unix because they all kind of do this. But notice that they all involve scheduling stuff. Or ignore doesn't really. We just throw the signal away. So the default actions are all actions that the kernel can take on behalf of the process without actually involving the process at all. That's kind of important, because this is the reason why the kernel can go ahead and handle them on its own. So if we've gotten through all of those steps and we can't handle, or the kernel couldn't handle it on its own, then it has to invoke the user process signal handler. And remember that this is actually the state of our stacks within doSignal. So we had the user process stack, it's got some stuff on it. We're in the kernel, so the user process's machine context has been recorded to the kernel thread. Okay, so we have all of that stuff. We have a few other details on the kernel stack because we're inside of doSignal, so that's why we have other kernel stack data at the very bottom. But this is the state of our system when a signal is being delivered. Now, running the signal handler is easy. We just go in and set the interrupted process's context to point to the signal handler. And we have the value of EIP to store because they gave us their signal handler. So we can go ahead and just stuff that into the machine context. When we return from the kernel, it'll automatically restore that information. So that part's easy. Except that the problem is, when we do that, we need to make sure we still get back to the user process wherever it was when the signal went off. So we need to make sure that we don't actually lose that information. Okay, so this is what I'm talking about right here. So the challenge is we need to set up a second context for the signal handler to use, and then we can preserve our process's machine context. The other thing that's interesting, another challenge, is that when we return from the kernel, remember that all of this stuff on the kernel thread gets thrown away. As we unwind from our system call or entering into the kernel, we have to make sure that we consume these details on the kernel stack. So hopefully this information and the previous thing indicate the solution, what the solution will look like. We just go ahead and create a new machine context, or we save I should really say we save the old machine context on the user process stack, because that'll be around. Okay. So we copy the CPU context of the process before it was interrupted onto the stack. A few other details as well that need to be stored. Okay, you'll notice we store blocked signals because we need to be able to restore the blocked signals when we return from the signal handler. A few other details. Yeah, so we'll talk about that in a second. Then the kernel goes ahead and modifies the machine context on the kernel stack to point to the signal handler. Okay, notice all it needs to do is set reg's EIP to the handler address, because now we want to go back to that instead of going back to the user process. And there's a few other details we need to change as well, because you'll notice we've pushed stuff onto the stack. So now we need to update our callers SS and callers ESP at the top to point to the new top of the user process stack. Okay. So of course we also need a stack frame for the signal handler, so we go ahead and push stuff. Now what's really neat about this is you'll notice that we have to push the signal number. That one's obvious. But we also need the sig info and the machine context if we are doing our advanced signal handling mechanism. Well, those things are already on the stack because we needed to save them anyway. So we can just put pointers to those things into the the sig action handler frame, the arguments, and then it can access that stuff. Okay, let me see if there was anything else I wanted to say about that. So this is how signal handlers are actually able to modify the process machine context in the signal handler, and then when it's returned, it all gets restored by the kernel. It's pretty clever. Okay, last thing to do. The signal handler at the end will ret. We need to return, and we need to go somewhere. We need to go back to whatever was interrupted on the process. Well, the problem is we need to restore the machine context. The kernel is really the one that's capable of doing that effectively. So we need to do a little bit of fix-up. There happens to be a system call, which you probably didn't know about, called sigreturn. Sigreturn is basically the thing that goes back into the kernel to handle the fix-up after a signal handler so that we can go back to the interrupted process. It's a system call, so you can see we basically have this little bit of code that has to be invoked. Move sysreturn system call number into EAX and then invoke int 80 or whatever it might be that actually, if we're going to do like a sysenter or something like that. Okay, and sigreturn, all it does is it takes that machine context off of the process stack and restores it. That's all it does. Okay, so that's how we do that whole thing of we're in the kernel, we jump over into the user process to execute the user function, the system call handler. We jump back into the kernel. That's sigreturn. We jump back into the kernel, restore the user process, and then go back. Now, notice that this kind of suggests that you could use sigreturn in other ways. You could put the appropriate information on the stack, invoke sigreturn, and happen to jump somewhere else in your program. That might be fun. If you wanted to do things really wild things like that. Generally, though, people don't even know that this occurs at the end of their signal handling. Okay, now last thing that happens before the signal is delivered to the user process is we have to update the caller's ESP. I mentioned that before. And so we go ahead and return from do signal. So it goes back to its caller. We eventually end up restoring the machine context, which is now the context that points to the signal handler. So all of this stuff gets unrolled, and we end up going back to the signal handler. So now that starts to run. Okay, Everybody see how that works? This is pretty cool. Now we're inside the signal handler. The interrupted process's machine context is saved safely on the user stack, maybe unsafely depending on how good the code is. And when we return from the signal handler, the kernel steps in, returns, restores the interrupted process context, and back we go to the user program. Okay, so same sequence of steps. We're all familiar with this because we talked about this last time. Sysreturn copies the process context that was interrupted back into the machine state, because now, remember, sigreturn, when it runs, will save the machine context of the signal handler. So we replace that with the interrupted process context. Then those things get reclaimed. And when the kernel returns, it will restore the interrupted process context and end up back at whatever the process was doing. Okay, does that make sense? This is the idea. Now, a few other details of this. One is that I may be blocked on a system call when a signal occurs, which means that I'm actually interrupting a system call, not just some random operation that the user process is doing. Okay, where I force a context switch, I preempt the process. Okay, typically what happens is the system will return EENTER for the system call. It was interrupted by a signal. Okay, now that's not always what it does, but that is often what it does. Because it turns out that there's a couple of calls where it can actually retry the operation. Read or write are examples of this, where it'll actually restart these if we haven't gotten to the point that important stuff is happening. So another one that's really complicated is nanosleep. Basically, if that's interrupted by a signal, then clearly I was sleeping, a signal went off, so I started running again. And so nanosleep will return EENTER and how much time it actually slept. Okay, so how do we actually achieve this? Well, it turns out that it's pretty simple, because the kernel can look at why we're in the kernel by looking earlier on the stack, on the kernel stack we're talking about here. So we would see, for example, in the interrupt number field on the kernel thread information, that the interrupt number was hex 80. We were inside of a system call. And of course, if you're inside of a system call, you can look at the register state to look at EAX and see what was the system call number that I was performing. Is it read? Is it write? Is it nanosleep? Is it something else? So it's pretty easy to tell I'm in a system call. I got interrupted by a signal. Okay, so that's all what I was saying already. So the kernel has a couple of options. Like I say here, depending on the process's configuration, and also, of course, the kernel's configuration. This obviously comes down to what the kernel wants to do. The kernel can do a couple of different things. The first one is it can just say, sorry, I'm canceling out your system call. All it needs to do is go back into the machine context of the interrupted process and write into EAX minus EENTER to say your process's system call was interrupted. Okay, so that when we return back from the kernel thread stack back to the user process, it'll say, oh, I got back EENTER, I need to retry. So that's one option. Second option is if the kernel is able to retry the operation, then it can do another thing. It can actually restore the EAX to the original system call number, back up the EIP to the int80 operation or the sysenter operation, and then return to the user process, and it'll simply retry the system call. Okay? So what we're doing is, since the kernel has total control, it just moves back to the instruction that causes the system call and causes it to occur again. Okay, so that's another interesting option that the kernel has. Again, people who are very familiar with IA32 assembly code will recognize that int80 is encoded as 2 bytes, hex CD, and then hex 80. I don't remember how sysenter is encoded or syscall, but the fix-up may be a little bit different for those instructions. Okay, So this is how we can actually interrupt or retry system calls based on signals being delivered. Okay, last detail. Signal handlers can use siglongjump. Basically what we're saying is, okay, the signal occurred, I want to terminate the signal handler, I want to jump back to some other part of my user program. Okay? We describe long jump and siglongjump as non-local go-tos. That is an accurate description. This is the state of the stacks inside the signal handler. That's why we have signal handler stack data, because that's whatever the frame is for the signal handler. And so we basically remember, I don't know if you remember set jump and long jump in great detail. Turns out that you could use long jump or siglongjump. Siglongjump happens to be strongly preferred because it has the ability to restore the block signal mask when the long jump occurs, which often is very important if you're jumping out of a signal handler. Because remember, the signal is already blocked inside the signal handler, so if you just long jump out, it won't, you'll never see another signal of that type until you unblock it. So siglongjump can take care of that for you automatically. Okay, so the question is, does performing a long jump or a siglongjump out of the signal handler break the kernel? Does it break the signal delivery mechanism? And an aspect of this that I think is valuable to consider is, well, okay, so I guess I'm not going to talk about it right yet, but I do on the next slide, I think. Why would a user process want to jump out of a signal handler? They would want to jump out of a signal handler because they don't care about restoring the old context of the process before the signal occurred. That's kind of a really important detail. If they want to jump out of a signal handler, it's because it's a big enough deal to the program that it wants to completely reset to an earlier state of the program execution. Okay? So that's going to be a really important detail. This is also why it's important to note that when a signal is delivered, we update the pending bit mask to say it has been delivered. We do that right at the beginning. So even if we jump out of the signal handler, as far as the kernel is concerned, the signal's been delivered. We don't care anymore. Okay? So the kernel doesn't need to do any further fix-up. Going back into the kernel from the signal handler was really only necessary on behalf of the process. The kernel was fine. It didn't care anymore. So yeah, like I say here, the kernel doesn't require the signal handler to return in order to complete the processing. The signal delivery is finished when it jumps to the user process's signal handler. Okay? The only real reason why it goes back is to restore the interrupted process's context and do a few other things. Okay? So siglongjump can take care of these things for us. Okay. So yeah, there's no state on the kernel stack, so we don't need to worry about destroying kernel stack information or anything like that. We're okay. So basically, if I long jump, or siglongjump really is what I would like to do, out of a signal handler, it doesn't have any effect on the signal delivery mechanism at all. It's kind of all on the user process at that point. Because there's no more information. The kernel's taking care of all of its work. The kernel doesn't have any state lying around that it needs to restore. It's moved it all to the user process. So it's completely on the user process if it needs to do that kind of thing. Oh, my slide number 2 didn't go up. I need to fix that. So yeah, why would a process long jump out of a signal handler? Remember that somewhere there will be a jump buff, or if they're writing a good program, it'll be a sig jump buff because they want to make sure that there's they're doing a sig long jump out of the signal handler. So that'll be a jump buffer that is in an active stack frame. And remember, that was a really key detail. It has to be within an active stack frame. And that'll record the CPU state at that earlier point on the stack. So what we're saying is we don't care about anything after it. We don't care about the interrupted process's context. We don't care about the stack, the signal handler's context. So we're saying we don't want to restore any of that stuff, so we just throw it all away with the long jump. We're perfectly fine with that. Okay. So not only do we not invoke sysreturn, we don't care about invoking sysreturn because we don't want to restore that state. We want to restore the jump buffer state. So that's why it's okay to ignore that step of the process. Okay? So let me just ask, because that's actually all that I wanted to talk about this, which is probably good that it went short because I don't know if my voice will last. But does anybody have any questions about this mechanism? It is pretty clever, pretty well designed. So this is basically how signals are delivered in operating system kernels and how we can do all of these clever things and support all of these clever things without actually messing up the kernel and with managing the various machine contexts that are in flight during this process. So, all right, next time, hopefully, if I don't lose my voice. Sometimes when I try to lecture when I'm sick, I lose my voice, and then you guys get like a week off because I can't talk. But what we're going to start talking about next time is actually kernel allocators. We'll have 2 lectures on kernel allocators because there's a variety of really interesting approaches that are used for managing memory inside the kernel. So we'll talk about that next time.